All right, so in this section, we're just going to take a look at some common motifs. I wouldn't bother memorizing these or anything like that. Really, the best way you're going to get this material is to just do some practice problems, and then it's just going to start coming naturally. So don't bother memorizing these, but just take a look at them, and just so you can kind of see and get a quick intro to this kind of stuff. So the first motif is having a lone pair next to a double bond. So here's some examples of that. Right, so first thing we can identify is the double bonds. Remember, this is just showing movement of pi electrons and lone electrons. That's all resonance is. And so to have pi electrons, you need a double bond at least, right? So we can identify the double bond in all of these. And then in all of these, there's also a lone pair next to all of these. This one's a little bit harder to see because we actually don't have to draw the lone pairs. My bad, I've got that negative there. But we do have lone pairs here, right? We have two lone pairs here, got two lone pairs there. We've got a lone pair on this nitrogen. And then this negative carb anion, there's a lone pair on that as well. And so we can draw some resonance structures here. We could move these lone electrons there and move the pi electrons, localize them on one of the atoms. Same thing down here. Same thing over here. And again, move the lone pair and then move the pi electrons. Move the lone pair and then move the pi electrons. You have to do this in one step because if you don't do this in one step, you're going to break the octet rule, which we can't do. And then you kind of want to be able to comfortably see what the result is going to be. So let's go ahead and draw the resonance structure for all of these. Oops. That one will look something like that. This one like that. This oxygen has gained electrons, so negative. This oxygen has lost electrons, so positive. This oxygen up here has gained electrons, so negative. This nitrogen has lost electrons, so positive. This oxygen up here has gained electrons, so negative. This carbon has lost electrons, but it was negative, so now it goes back to being neutral, right? And so this is just a common motif that you'll see, and really the best way to get it down is to get some practice. Another thing we can commonly see is a carbocation, so a positively charged carbon next to a double bond. So something like our allyl cation, right? We have that positive charge there. And we can resonate back and forth with the other compound, right? Here we just need one arrow to show this. But it can get more complicated than that. You can have conjugation further throughout a molecule. So let's take a look at something like that. Check out this carbocation, for instance, right? We can move this pi bond over here to move our carbocation to the center. Right, this carbon over here just gained some electrons, so it was positive, now it's neutral. This carbon over here just lost some electrons, so it was neutral, now it's positive, and then this double bond is unaffected. But now we can do the same thing we did with the other double bond, with this double bond, so we can move that over. Right, this part of the molecule was unaffected, so that's going to stay the same. This carbon was positive, now it gained electrons, so it's going to be neutral. And then this carbon was neutral, but now it just lost electrons, so it's going to be positive. So that's just something to keep an eye out for. Oftentimes there are multiple resonance structures, right? Not just two, but maybe 3, 4, 5, 6, 7, 8, 9, 10, a whole bunch, right? Another thing we want to keep track of is a lone pair next to a positive charge. So something like this, right? We can move the electrons from this oxygen onto this pi bond here to form our neutral structure. Another example would be something like this, right? This oxygen here has a lone pair. We can move this lone pair over here. And now our oxygen is positively charged. As always, you need to be careful to not break the octet rule. So for example, we have our kind of nitrite motif here. And we could think about, we have this kind of positive negative charge, so we could draw a resonance structure. But if we just try to move this in one step, what ends up happening is this nitrogen now has 5 or 10 valence electrons, right? 5 bonds, 10 valence electrons, and that's a big old nope. So we can't do that in one step, but if we move those electrons over and then in the same step broke this pi bond and put that on the oxygen, then that's okay. Right, this is okay. So just be careful of breaking the octet rule. Another thing to keep out for is pi bonds between different atoms. And so this one's pretty simple. These don't always show kind of the best resonance structures, but they are there, right? Anytime you have a pi bond and you have 2 different atoms, you can have unequal sharing. And so you can show this through a resonance structure, right? We can move those electrons up there, and then we end up with a negative oxygen and a positive carbon. Same thing with nitrogens as well, right? We could move this lone pair up to the nitrogen. We want to move the pi electrons to the more electronegative element, not the less electronegative element. And finally, number 5 is conjugated pi bonds in a ring. And so we'll talk about conjugation a lot. Conjugation just basically means that you have alternating double and single bonds. So you have a carbon that's doubly bound to a carbon or something else. It doesn't necessarily have to be a carbon. That's then singly bound to another element and then another double bond, right? So we have this kind of alternating motif where we have double, single, double. The most popular example of this is going to be benzene. Right, so it looks like we have alternating double bonds, right? That we have a single bond, then a double bond, then a single bond, but that's not really true because we can draw a resonance structure in which everything's kind of the opposite, right? Everything's flipped. All the single bonds become double bonds, and all the double bonds become single bonds. So in real life, they're all the same bond length and all the same bond strength. So those are just some common motifs to keep an eye out for. Really, don't try to memorize this. Don't try to memorize this list. Just get some practice down, and it'll start coming naturally.